In today's class, we are going to go through MOS device operation. I expect all of you to know quite a bit of this, okay, because this is one of the prerequisites for this course. So, what we'll do is we'll try to go, when I'm covering something new, like for example, short channel MOSFET effects, I'll try to cover it in a little bit more detail. Otherwise, we'll try to move a little bit faster. If you have any questions, you can come and ask me after class. Is that clear? Okay. So first we'll look at the long channel MOS operation. So you know you have three regions: off, triode, also called the linear region, and saturation region, right? So in the linear region, the current to voltage relationship is mu and Cox W over L times VGS minus VT times VDS minus VDS square over 2. Right? You guys should, this should be in, at your fingertips, right? All of this. So, for small VDS, you can approximate, you can neglect VDS squared over 2, and ID is VDS, right? So, this is something like a voltage controlled resistor. Right, so it has a linear relationship with your VDS. Okay, okay. Then in saturation, it's half. I'm covering all of this for an NMOS. Obviously, the same thing holds for the PMOS. Right, half mu and Cox W over L VGS minus VT the whole squared. So it's a square law dependence. Right, this is for a long channel device, and you should also know a little bit of the MOS device physics, right? So what happens to the channel when it is formed? We covered a little bit of it last week. So you have a so you have the oxide P, right? So obviously when it's off, there is no channel. It's just the bulk, right? So nothing, no current flows through the device. Then once the VGS crosses VT, you have the channel, and the channel is uniform when VDS is 0, and slowly so let's call this the source, let's call this the drain. So on the drain side, the channel starts to pinch off. So in the boundary between the triode region and the saturation region is when your pinch off happens, right? After that, you no longer have a channel at the drain side, you only have it at the source side. Okay, okay. So let's start looking at so with that background, let's start looking at the capacitances of the device. So you have probably covered this a little bit in your analog ICs course. So what you do is at low frequencies, you assume there are no capacitances for the device. So you just assume input is open circuit, you have a transconductance GM, you have an output impedance, right? So at low frequencies, that's good enough. At so-called high frequencies, so you need to consider all the appropriate device capacitances. What are high frequencies? So we'll see that each, depending on the size and the bias current and so on, the device has what is called a transition frequency. So this so-called low and high frequencies actually is relative to that transition frequency FT. Okay, so we'll see the expression for FT. So you need to consider all appropriate device capacitances at high frequencies, right? So what are the device capacitances? So let's call this the source, the drain, this is the gate, and this is the bulk. Okay. So what capacitance do you know of? Let's see. So you have a source to bulk, drain to bulk, junction capacitances. So you have some capacitance here. Okay, and remember that for any MOSFET, you actually have your gate actually doesn't exactly end where the source or drain begins. So you have an overlap region LD, and then so your actual length is L minus 2 LD, right? So then what happens? You have a gate to source and gate to drain overlap capacitance through the oxide, Is that right? Okay, and then let's say you have a channel. Let's say in this case it's in saturation. Okay, now remember that this is an N-type channel and this is a P-type substrate. So there's going to be a depletion region between the two. Okay, so you actually have a channel to bulk capacitance also. Okay, so what we'll do is we'll just draw a table with the different capacitances of linear and saturation. Okay, so let's name some numbers here. C overlap is WLD Cox. Okay, and we are going to say CGC, gate to channel, is going to be Cox WL effective, and CCB is some value. I don't need to write it out, so it has some silicon over XD, the depletion region, W times L effective. Okay, the full expression for XD is, I'll give it in the notes, you don't need to know it for now. So you have some CCB. Okay, so let's look at the different caps. So what is CGS when it's off? It's just the overlap capacitance, right? So you only have C overlap. And similarly, when it is linear, in linear region you have the full channel. So you have C overlap plus. So now once you have the channel, so you try to, so your capacitance, right, between the gate and the channel is going to be WL effective Cox. You're going to split that because there's an equal channel on both sides. You're going to split the capacitance halfway between the drain and the source. Okay, so CGC over 2, and in saturation you can show that it is C overlap plus, so once you have pinch off, right, you can show that the capacitance is 2/3 WL effective times Cox, or actually let's just use the abbreviation, so 2/3 CGC. Okay, how about CGD? It's going to be very similar, right, except in off it's the same, C overlap. In linear it's the same, C overlap plus CGC over 2. So those two cases are identical for the drain and the source. In saturation you only have C overlap because you no longer have the channel on the drain side. Okay, so then let's look at the gate to bulk capacitance. So when it's linear, when the transistor is operating, there is no direct capacitance, so it's 0 for linear and saturation. And in this case it's not exactly quantifiable, but it's somewhere in between. It's somewhere in between CGC parallel CCB and CGC, somewhere in between that. Okay, okay, then CSB and CDB, those are the drain to bulk and source to bulk capacitances. So these are the 5 capacitances of the device. So when it's off, it's just the, so let's call this CJSB, the junction capacitance, CJDB. Okay, so when it's off, it is just going to be CJSB, and when it's linear, you're going to have CJSB plus CCB over 2, right? And here CJSB plus 2CCB over 3. Similarly, at the drain side, you have CJDB plus CCB over 2 in the linear region, and of course in saturation it goes back to CJDB. Okay, because you no longer have the channel on the drain side. Okay, and of course since we have let's also Cox is epsilon ox over Tox, right? So that is the oxide capacitance. Okay, so so if you look at your MOSFET, so you have the gate, drain, source, and you have the bulk. So remember, don't neglect the bulk. Anytime you have a transistor, make sure you bias the bulk properly, okay, even in your simulations. Otherwise it will cause all kinds of problems. So you have gate to source, gate to drain, you have CDB, CSB, and finally gate to bulk. So these are the 5 capacitance we'll consider. So let's look at the small signal model of the device now. So first of all, you have an RG, okay, a gate resistance. So it's never going to be ideally capacitive. You are going to have some kind of gate resistance, okay. Then, so let's okay, how do we do this? Okay, so let's add the CGS first. So you're going to have VGS across this, and then what do you have? Okay, so let's call this the drain, the gate, and let's call this the source, and you're going to have the bulk here. Remember, you also have a bulk to source voltage, and because of that you have a GMBS times VBS. Remember this, right, from your devices? And then you have your R out of the device, okay, okay, and then CGB, CSB, CDB, okay. So this is the small signal model of the transistor you are going to use in most cases, okay. There are some cases you might be able to neglect some of the capacitances. For example, if you have a common source, your bulk and source is the same voltage, you may be able to neglect GMBS and your, for example, CSB, right. But what you will find is there are some cases where you might be able to neglect CGB, but in most cases you will have to consider it, okay. But the most important thing to note, CGS very important, CGD very important, CDB very important. All these 3 are going to be very commonly important in a lot of cases, okay. Okay. Gate to bulk. Gate to bulk depends on the CCB in some cases, doesn't depend on the in some cases. This is just the capacitance. So we looked at the value of each one of these 5 in the previous slide, right? Okay. Okay. So now what is the GM? Dou ID over dou VGS at when VDS is held constant, right? Yes. Yes. This GM is different than? Yes. One of them is GMVGS, other is GMBS, VBS. Yes, that's right. So the GM depends on the gate to source voltage, the GMBS depends on the bulk to source voltage. So GM is, so you have a lot of expressions, right? You can write the expression in terms of the current, in terms of the overdrive, and in terms of both, right? So you can look at that, okay? And expression for RO is dou VDS over dou ID, which happens to be 1 over lambda ID, right? So this also you know, right? Okay. How do you find out GMBS? Right? How does this come about? So the current to voltage relationship we showed, does not explicitly have a dependence on VBS, right? So where does it come from? VT, right? So VT is the only one which depends on VBS. So this is some eta times GM, where eta is gamma over 2 phi f times GM. Okay? Okay. So now we'll look at what is called FT. Have you studied this in the analog ICs course, the FT of the transistor? You have, right? Okay. Do other people know about it? Okay. So FT is called the transition frequency. Okay. So that is the frequency at which the current gain of the transistor goes to 1. That is how it's defined as, right? Okay, and of course we quite often use omega t also. Okay, so let's try to calculate what the, so you're going to, let's put in a current here, IN. So you want to find out the short circuit current, right? Let's call this the drain ID, drain current ID. Okay, so what we are going to do is, we are going to neglect, so the common definition of omega t or ft neglects drain to bulk, some of the capacitances. It neglects the drain to bulk capacitance, it neglects Rg, and it takes into effect CGD only for input impedance. Okay, nothing else. It doesn't take the effect of the feed forward effect of the signal. Okay, if you do that, what is that? You have Gm over, so In times omega times CGS plus CGD is the voltage at the between the gate and source. So ID over In is okay. This is the expression for ID over In, and you want to set this to 1, right? So if you set this to 1, you get omega t is Gm over CGS plus CGD. So therefore, now you can write ID over In at any frequency is nothing but omega t over omega. Is that clear? Okay. And for long channel devices, you can further approximate your omega t, right? So you're going to do, you know, CGS is much larger than CGD because CGD is just the overlap capacitance. CGS is comes through most of the length of the device. So let's neglect it. So quite often you would approximate it as Gm over CGS. So what is Gm? Mu Cox W over L times VGS minus VT. And what is CGS? 2/3 WL Cox. Right? So omega t is over L squared. Mu n VGS minus VT over L squared. So what does this mean? If you want to increase the omega t of the device, which you will quite often want to do when you are operating at higher frequencies, right? So if you want to increase omega t, use the minimum length, okay, and maximum overdrive. So those are the two things you want to do. VGS minus VT is the VD sat of the device or the overdrive of the device. Okay? Okay? Have you heard of F max or W max, omega max? Okay, so this is the frequency at which the power gain of the transistor. So this is actually more important in many cases. Okay, and what you'll find is this is actually different from the omega t. Okay, so this is called the this is the frequency at which power gain goes to 1, power gain of the transistor. Okay, so let's see what the power gain is. So first, to calculate the power gain, you need to know what the output impedance is, input impedance is, and so on, right? And the other thing you're going to do is, you're going to assume that input and output are conjugate matched, especially the output, okay? Because input, it's a current source, okay? So you're going to assume it's pumping directly into the transistor, but the output, you assume it's conjugate matched, okay? So first of all, what is the output impedance at higher frequencies? So you can calculate it out, but it turns out to be this, okay? Gm times CGD over CGD plus CGS, which is omega t times CGD. So you're going to conjugate match to this at the output. Okay, so you're going to do GL equals G out. So when you do that, what happens? Half the power goes into the load and half the power gets burnt in the device itself, right? So if you want to calculate your power gain, okay, so what is the current, what is the drain current? You know it's omega t over omega times IN, right? And half of that current goes through the load, right? Whole squared. And then of course you're going to have a half factor because peak to RMS and so on, right? This is the power dissipated in the load. It's clear? Is that clear to everybody? ID is omega t or omega times IN. Half of that current flows through the load. So I squared times R is the power, and of course you have the 1 over 2 factor because peak to RMS. Similarly, what is the input power burnt? It's IN squared times, you have a gate resistance RG, and of course half of that. Okay? So this is what the power gain is. So this is actually PL over Pin. And if you set this to 1, you can find out your omega max. Yes. It is just a matter of, I guess, bringing it down to simpler terms in terms of omega t. So this is actually an approximate relation. It's not the exact relation. Even if you look at omega t, right, you also neglect quite a number of effects because you actually have a feed forward effect through CGD for the signal. You neglect all those things because you want to come down with simpler expressions, because the main idea why you want to come up with expressions for omega t, omega max and so on is to get some insight into how the device is going to behave with respect to, let's say, the length, the width, the overdrive and so on, right? So you neglect a number of things, and in this case you are neglecting the CDB and a bunch of other capacitances.
Also GMBS, that is significant.
Again, yes, again you neglect GMBS for these cases. Okay, in this case GMBS doesn't come into being because you are considering a common source topology, right? But in reality you will have to consider GMBS, because if you look at these short channel transistors, your GMBS is quite often 20% of your GM.
Also in the differential case, you will always have the body may not always.
Yes, absolutely, that's right. So you could have a case where body is not at the same point as the source, right? So if you want to calculate more accurate expressions, you can, okay? But this is just to gain some insight into the dependence of omega max and omega t on multiple other parameters, okay? Okay, so your omega max is half of root of omega t over RG CGD. Okay, so this is a useful thing to remember. Okay, and then we'll quickly So if you see the transistor, right, at higher frequencies, you also have what are called non-quasi-static effects. So quasi-static, you assume that there are no transit time. Once the electron goes from the source to the drain, it goes there immediately, and the effect of the gate is felt immediately. In reality, that doesn't happen, especially at higher frequencies. Okay, so that actually comes up as an impedance at the gate. So you actually have a gate impedance Gg, which happens to depend on frequency. Okay, omega square Cj squared over 5 Gd naught, and Gd naught is the Gd at Vds equals 0. Okay, so we'll come back to this later in one of the next few classes, because what you'll find is, so if you can show that Gd naught is approximately Gm. Again, we'll show that in a later class. And the thing to know is, if you make that approximation, you can come up with an expression in terms of omega t. Okay, so what that means is the non-quasi-static effects come into play when you get closer and closer to omega t. Okay, usually at normal frequencies you won't see any effect on this, but what you'll see is, even though the Gg effect, the impedance effect becomes more prominent at higher frequencies, what you'll see is, when we come to characterize the noise of the device, you'll find that this Gg actually exhibits noise at your frequencies of interest. Okay, and of course it does increase with frequency, the noise too. GD0 is just the impedance of the device in the linear region. Okay, it's a GDS, right? It's a current control voltage controlled resistor, right? But you call it GD0 because it is at VDS equals 0. Okay, so GD0 is just the resistance of the the 1 over RD0 is the resistance of the device at VDS equals 0. Okay. Okay, so then we'll quickly look at scaling, right? And what happens to different parameters when you scale the length of the device, when you go from one process node to the next process node. So what do you do in scaling? You assume all linear dimensions scale by a certain factor alpha. Okay, go down by a factor of alpha. All dimensions go as 1 over alpha. Okay, let me just, I guess we'll write it down later. But so you scale all the dimensions by alpha, you scale all the voltages by alpha, right? So your VDD and your threshold voltages, right? And then to keep other things in to keep other things working properly, you also scale up the doping levels by alpha. Okay. Okay. So what that means is, so what happens when you scale the VDDs and the VTs by alpha, and you scale the dimensions by alpha, what that means is your electric field in the device stays constant. So it's also called constant field scaling. Okay. Okay. So what happens to let's look at what happens to the different parameters of the device. So I have actually a number of things. I'll put them up in the notes, but we'll look at the important things in class. Okay. What happens to the current? Okay, so that is your original device. So first of all, Cox is epsilon naught over Tox, right? So what does that mean? The scale Cox. So remember, your dimensions go down by alpha, right? So your Tox becomes Tox by alpha. So what that means is your Cox actually goes up. Okay. By alpha times Cox, the old Cox. And in general, what you'll see is most of the capacitances go up by alpha because you are changing the dimensions. So now, if you look at the current, Okay. Right. So this is the expression for the new ID, and you know you can cancel out the multiple terms, and you can clearly see that this is your old drain current over alpha. Yes. Yes. So you're assuming that you're also going to see. Remember, we're going to scale all the voltages. So you're assuming gate source voltage also scales at the by alpha. This is technology scaling, right? But the main reason we want to go through this is we want to find out what happens to GM. We know what happens to the capacitance, so we want to find out what happens to omega t, and you know that's the main reason why we are looking at scaling right now. Okay, because you'll need to know this for your this thing, because in general if you want to choose a particular process you need to evaluate omega t, and you may have to compare it across processes. Okay. Okay, and now we have a bunch of other things, but let's look at transconductance. So this is your original GM, right? What is GM alpha? Right? So this is the same as your old GM. Yeah, that's right. Okay. So now, so what happens to your FT? Do I have FT here in the notes? I don't have FT here in the notes, but I have. Why didn't that thing? Okay, because I have. Okay, that's right. Okay, I think we won't consider FT for now because we need to go into the short channel, and then we'll compare FT. Okay. So let's look at short channel operation of the MOSFET. Okay. So now remember your square law relationship, right, between ID and VGS minus VT. Okay. So how do you derive it? One of the equations used in deriving it is you want to find out the drift velocity of the electron in the channel. Okay. And when you do that, you actually assume along the, if you take a dimension y along the channel, right, you assume that the drift velocity is linear with your electric field along the channel. But in reality, this is true for low electric fields, but at high electric fields it's not true. So if you look at the actual behavior, so it goes something like this. Okay. The drift velocity versus E goes something like this. Okay, so at low electric fields it's valid, at high electric fields it's no longer valid. Okay, and it ends up, it's called the scattering limited velocity. Okay, so what we'll do is, and your scattering limited velocity is mu n times EC. Some people use ESAT. So if you're EC, yes. Yes. But okay. So we'll look at it next. We'll look at why we are interested in this short channel. In reality, what you'll find is, even though you're talking about it happens only at very high electric fields, you're trying to keep the electric fields constant. The actual short channel effects do not depend exactly on the length of the device. They actually depend on a ratio of parameters. Okay. So we'll look at what ratio of parameters they depend on. Okay. and it happens to depend on the ratio of the electric field and something else. Okay. So what you can do is you can try to approximate you try to get a better approximation, okay, for your, by rewriting your drift velocity as, why do I keep doing this, mu n e by EC. So you try to, instead of a linear relationship, you try to get closer to what is real. Okay. And your EC is defined as the point when your drift velocity goes to half of what it was if it were linear. Okay. If it was linear, you would get only mu n EC, but at E equals EC, you actually get mu n E over 2. Okay. So when it goes to half of the linear value. Okay. Now if you look at a long channel, right, long channel device, so we'll rewrite the expression slightly differently. You know that VD sat is just VGS minus VT, right? So we'll rewrite it this way and try to find out how we can modify the current voltage relationship of the MOSFET in short channel operation. Okay. So what you can also show, we won't show that in class, but if you want, you can look up the reference. You can show that your VD, okay, so for a long channel, your VD sat is nothing but VGS minus VT. Okay. In reality, your more accurate expression for your VD sat is this is a more accurate expression, which is VGS minus VT in parallel with LEC. So which is okay. So now what we'll do is we'll replace this in the current to voltage expression for VD sat. Right. So you can show that this is the expression for the current. So now what does this mean? So this obviously goes to the long channel value when L times EC. So what you're going to do is compare, let's say VGS minus VT over L and EC, or VGS minus VT and L times EC, right? So anytime this ratio, right, VGS minus VT over L to EC, okay, is small, you can assume that your long channel approximation is valid because this will reduce to VGS minus VT. But the minute this starts getting close to EC, okay, then you have to start worrying about these short channel effects. Is that clear? Okay. So now you can also rewrite this, you can also rewrite ID in a slightly different form. WCox okay, so you're going to rearrange the items inside here. You know VSEL is mu times EC and so on. You can rewrite it like this. Okay, so you may not be using these for hand calculations, right, very often, but you want to, the main idea of trying to do this is try to understand what happens in the short channel regime, right? They are approximations, but they are very useful approximations. Okay, so what happens when you have very deep saturation, right, deep velocity saturation, what happens? You pretty much forget about VGS minus VT here. You're only going to have L times EC. Okay. So what do you see? Something very significant happened, right? What happened? First of all, your drain current is no longer dependent on the length of the device, okay, which is very significant, because so far if you change the length, it makes a big difference, okay. So one thing to note is it does no longer depends on the length, okay. What is the other thing you notice about this? Sorry? Exactly. So the ID to VGS relationship is no longer a square relationship, it's a linear relationship, okay. So those two changes are very important for us. Okay, so now let's look at the yes. No, EC is actually a constant value. It's E which depends, right? Not EC. So remember, we define EC as, so you have a scattering limited velocity. EC is related to scattering limited by this equation. So EC is actually a specific value. So typically it could be some value. I think I have it in the notes. It's somewhere around 1.5 into 10 power 6 volts per meter. Okay. Okay, so now you have this current to voltage relationship, right? So now we are going to find out what happens to omega t. Actually before that, so we want to calculate GM and CGS, right? So what is your GM, new GM? Right? So you only have a linear relationship. So your GM no longer depends on your VGS minus VT. It only depends on the width. What about your CGS? CGS remains the same, right? So there's no reason to assume that the capacitance itself has changed. Okay. Yes. Pinch off has happened. You're assuming all in saturation. No, you see, the velocity saturation is independent of your this thing. So you're assuming velocity saturation in the saturation region of the MOSFET after pinch off, right? So those two are two different effects. Okay, so you just divide GM over CGS. It has nothing to do with pinch off, right? Velocity saturation has more to do with the field, right? So at high electric fields, or rather, obviously we saw it happens, it's a ratio of VGS minus VT to L times EC, right? So that has to do with the electric field inside the device, whereas pinch off has to do with triode and going into saturation. So here we are all looking at velocity saturation inside, during MOSFET operation in the saturation region. So that is saturation in a different sense. Okay, the same word is just used in two different senses. That's all. Yes. When what is very small? Not necessarily, because if VGS minus VT over L, let's say you have a very small VGS minus VT, right? And obviously if you have VGS minus VT to L is very small, it is actually not in velocity saturation at all, right? Yeah, because EC is a fixed value. So you are going to compare this VGS minus VT over L and EC. When this ratio is very small, right, you don't have any problem. Only when it's large, it's a problem. Okay, so if you compare this to the previous case, what do you see? Earlier, what was the, so one thing you remember is, Omega t used to depend as, let's look at the earlier value. This was the earlier expression, right? Omega t was depended on Vgs minus Vt and 1 over L squared. What do you see here? What you now see here is it no longer depends on Vgs minus Vt. Okay? So for a normal long channel transistor, if you increase the overdrive, your omega t actually increases. But that is no longer the case when short channel effects are predominant. Is that clear? And so the only control you have is actually the length of the device. And it doesn't go as 1 over L squared, it now goes as 1 over L. Okay? And of course, so obviously what this means is it doesn't depend on bias conditions and so on, right? Vgs minus Vt is one measure of the bias condition. So this doesn't depend on the bias at all anymore. And one last point to note. So PMOS transistors, okay? It so turns out this EC and scattering limited VSCL and so on are dependent on the charge carrier, right? Because it happens due to some physical device effects. So it turns out that the EC or ESAT, sometimes it's called ESAT, is much higher for a PMOS because holes are the charge carriers. Okay? It shows velocity saturation at higher fields. Okay, so let's stop here. It's already 9:50, so let's stop here. We'll continue tomorrow morning. We are going to have a class. Okay, 8 o'clock, and we'll just take attendance just now.